our rectangle class, for example, has a height and a width. And when we want to use that class, we can say rectangle R1, comma R2. We can construct those as usual. And then somewhere we could say R1.h equals 5, R2.h equals 17. And this is an instance of a rectangle, R1. This is a different instance of a rectangle, R2. R1 has its own copy of this variable h, which we've set equal to 5. R2 has its own copy of h, which we set equal to 17. These are different variables. Okay, so these are what we can actually call instance variables. And that terminology refers to the fact that this variable belongs to each instance of a rectangle. So anytime you make a rectangle, you get a new copy of these instance variables. And that's the kind of variable we've been dealing with all along. There's a different notion of a variable, which is what we can call a class variable. And a class variable, this is something we're going to prefix with the keyword static. So static int, I don't know. Yeah, I don't know what to call it. Rectangles are special.
Max density.
Yeah. We'll just call it special. So, instance variables, you get a copy for each instance. Class variables, or statics, there's a single copy for the entire class. This is a class variable. So what does this mean? There's a class called a rectangle class, okay? There's also instances. You can have 1,000 different instances of that, but there's a single class itself, okay? A blueprint for making a rectangle. Special is a variable associated with that blueprint itself, with the class definition itself. It has nothing to do with any particular instances. Now, you're not supposed to do this, but if you were to do the following, r1.special or r2.special, they refer to exactly the same variable. Okay, you don't get a different copy of this for each instance of a rectangle. There's a single copy of this stored somewhere under the heading of here's a class variable for the class rectangle. Okay, but we're not supposed to access class variables using objects because it's deceptive. So the way you're supposed to access a class variable is actually with the name of the class itself, rectangle.special. Right, so this will refer to this one copy of that integer. So it's a bit like a global. Okay, it persists. It's a bit like a C static in that it survives outside of any particular instance of a rectangle. But the more important part of this is that you don't even need an instance of a rectangle to access this variable. So, for example, it may be uppercase. But there's a field in the math class called pi. I just rebooted, so this is going to be a little painful for a minute. Surprising the math class brings up the Java classes first.
Like, I hope I'm not a third grader.
Yeah. So yeah, so uppercase pi. So there's a field called math.pi. Okay, and it's defined to be a static double. Which means there's a single one of these. And it's part of the class itself, right? They found the problem with the temperature control in the rooms, by the way. Cold water wasn't being chilled when it was being distributed to buildings. So I don't know if they fixed it or not, but they know about it and they're trying to fix it. So let's make a static stuff project. Alright, so we've done this before, or we've done something like this. Right, we can use math.pi to get to the value of pi. Consider this. I can make a math object. Oh, bad example. Positive infinity. All right, so we can put it. We have an infinity value, and positive infinity writes a static double. Okay, so think about this. So I'm going to create a double object. And doubles need a value to construct. So I'll just construct it with a 0. And then I can say d dot positive infinity and get to my infinity value. But it's yelling at me, and I had to do some useless work in here, right? I had to create a double object. And I don't really need a double 0, but I created a D as a double 0 simply as a way so I could access this field. Okay? And that's a ridiculous thing to have to do, because I'm not doing anything with this D object except using it as a way to get a hold of this field. Right? And it's yelling at me because it's telling me that this is actually a static field and it should be accessed in a static way. So this mechanism lets us say the following, right? Name of the class dot field, and then you don't have to do this kind of thing. So this comes up sometimes with fields, but it comes up more with methods. So methods can be class methods or instance methods. So we can have a rectangle class. heights and widths and stuff like that. And suppose that somewhere inside here we want to supply a method for doubling a number, right? So we could say public integer double integer arg. So part of the rectangle class includes this handy method for multiplying a number by 2. And this method is set up to take an argument and return twice that argument. It's like a C-style function, okay, that you pass an argument to and it comes back. It's not an object-y kind of thing. It's not doubling the height of the rectangle or the area of the rectangle. It's really just a convenient method that we might want to use if we have a number we want to double. We can say something like y equals double of x. But double is part of this rectangle class, so we need to do something like rectangle r equals new rect. And then we could say y equals r dot double x. And the mechanics here are r is an object of type rectangle, and rectangle has an instance method called double, so let's run the code in double, pass it an x, get back a y. But this code is not using anything about this particular rectangle that we're using to invoke it. Right? So we could instead make this a static. A static int rectangle. And then we could do the following. Right, and we don't need an instance of a rectangle to access this method now. And this is what's happening when you say something like math dot square root, or when you say thread dot sleep. So statics are a way to provide code that can be accessed, or variables that can be accessed without having to have a particular instance of that class. Okay, so it's a class method. It belongs to the class itself as opposed to belonging to a particular instance. So with that in mind, we can talk about this.
Oh, is it backwards?
Yeah. Alright, so what is all of this stuff? So we're inside some class. And somewhere inside here, we've got this public static void main. And remember, when you want to execute this, you say something like Java my main. So what the Java command does is it looks for a static method called myMain.main with a signature that's expecting an array of strings. Okay, and that's the way that your code starts to execute when you say Java name of a class file. It goes into the definition of that class, that's the .class file, and it looks for a static method named main. And this only works because there's an agreement that main is the name of the static method that's going to be run by the Java command, right? Otherwise, you'd have to say something like Java my main space and then the name of the method you want to actually execute, right? So main is by convention the name, and it doesn't create an instance of your my main class. Okay, it just uses that class to access the static method. So it's got to be static. If it wasn't static, you'd have to actually create a myMain and then, you know, myMain x equals new myMain, and then you could say x.main. Okay, so it accesses it statically. So public, it's accessible outside of the class to the JVM in particular. Static, you can access this with just the class name. Void, by definition, is not returning anything. That's the name of the method. That's the type of the arguments. But there's a good chance this is the only place you're going to find yourself writing the word static in making code in this class. Right, so it's not necessary except in the main. There's cases where it makes sense to use a static, but outside of when we're deliberately trying to exercise that, you're generally not going to need to use the word static. But you can stumble into a belief that static is what you're missing in your code. So inside your main is a static method. If I try to do certain things inside main, I'll get an error message from the compiler saying cannot make static reference to non-static object. And one of the fixes is make the thing that you're trying to access static. And this sets you down a path of making more and more of your code static, right? And it sort of pushes the error further down the line. It's usually not the right solution. So if you're getting errors from the compiler in your main program complaining about non-static references or static references, right? Step back and think about this idea that there's not an instance of your main class in play here. Okay, there's just an execution of this static method as part of the class. But when you're running this, you haven't actually constructed a myMain class. Okay, so you don't have an instance of a myMain when your program is running. And that's usually where these troubles come from.
Is it kind of like a no reference exception then?
It might be if it actually lets you compile it, but these will usually be compile errors. And I tried to come up with an example right before class, and of course when you want it to fail, it doesn't fail. So I didn't come up with an example. But if and when you get one of these, right, feel free to post it on the discussion board, and we can talk about specifics. All right, so that make basic sense? And like I said, you probably won't need to do a lot with statics, other than when you say public static void main, which you'll be saying in your sleep eventually. All right, let's look at Towers of Hanoi. Because this is a pretty fun use case for threads. So one thing we do with threads is I say it doesn't sound like Tina. So threads let us do two or more things at the same time, right? And typically when you're doing graphics, right, this is a case where you have something running that's doing some kind of calculations that affect what you want displayed, and then you also have something that's actually displaying your information. And maybe you've got some widgets, some buttons, or some sliders you can use to control how the information is being displayed. And all those things probably want to be in their own threads. Okay, if you did everything in a single thread and you've got a set of code here that's calculating prime numbers, for example, and then displaying some information, if you never exit that thread, there's a chance that your graphics are never going to appear. Because remember, we don't get to paint objects, we get to say repaint. We get to say, when you have a chance, call the paint method for this this component. But if we're CPU bound in a chunk of code, that may never happen. And when you click on a mouse event, when you click on a button and you're inside an action listener, you can do all kinds of things in there, but until you exit from that code, there's a chance you're not going to respond to other events. So multiple threads goes along with the idea of event-driven code. So let me just show you a use case for Towers of Hanoi. And there's some details in here that are annoying and not really critical. But remember Towers of Hanoi, the solution. So you remember the setup, right? We got disks, we got poles, and we're trying to move all the disks from one pole to another. And the recursive solution was we're trying to move 4 disks. Well, if we can move 3 disks, move 3 disks over here, and then move the biggest disk here, and then move those 3 disks back to here. Okay, so if you can solve this for n minus 1, you can solve it for n pretty trivially. So the solution is if you only have 1 disk, just move it from the from pole to the to pole. Otherwise, move 1 fewer disks from the original pole to whatever the third pole is that you're not using, and then move the biggest disk from the from to the to, and then move those remaining disks from that third pole to the destination pole. Okay, so we've coded this up before and looked at it. And the only twist here is we're going to display graphically what's going on with each of these moves. So the show move used to just do a print line that just said move from this pole to this pole. So instead what it's going to do is it's going to update a data structure. It's just a 3-dimensional array called poles. So we have poles, bracket 0, bracket 1, and bracket 2. These disks are numbered. Okay, so 1 is the smallest disk, and then n is the nth disk. And this is simply an array showing which disks are on pole 0. So originally this might contain the numbers 1, 2, 3, 4, 5, 6, 7, 8. And then there's also a pole n, which tells you how many disks are on each pole. Alright, so this is the size of the array poles bracket 0. This is the size of the array poles bracket 1. It's the size of the array poles bracket 2. And poles bracket 0, 1, and 2 are each arrays of integers showing the disks that are on their respective poles. So poles is a 3 by 64. We can only go up to 64 disks. Pole length is an array of 3. Keep track of the number of moves. This is going to run as its own thread, so it extends a thread. And we're going to remember the identity of who created us, which is going to be this other class Towers. That's the main J-frame. And so when you say start on this thread, the run code will execute. This initializes your setup. So pole 0 gets all of the disks on it, and has a length of however many disks you have. And then pole 1 and 2 have a length of 0. And then we set a flag saying we're running, and then we solve the problem for that many disks. So numDisks, like everything else, is a method in here that'll tell us how many disks we're working with. So that's the workhorse, but it's actually the easier of the 2 Java files. Towers is just all of this gibberish related to making a GUI, but let me show you the design of it, because that's a little cleaner. So we've got a go button, we've got a speed slider, we can say how many disks we want to use. It'll tell us how many moves we've taken, and we've got a turbo button if we want to go really fast. And the only critical details in here, let's see, so we can find out what the current speed is. So 0 is the fastest, so if the turbo button is pressed, your speed is 0, otherwise it's whatever the current speed variable is. And the current speed variable starts at 2500. So that's just to slow it down so we can watch what's happening. Save data is used to pass data from that main thread to this class. Okay, so it just takes the arguments, which was the number of poles, the pole length, and the number of moves, and saves those in local variables. Number of disks reads this text field and parses it as an integer and returns that value. That's the number of disks. And then the paint method does all the painting. So it draws 3 poles. And this is typical of what you find in these kinds of sort of hand cobbled together graphics outputs. There's lots of mysterious numbers, right? And this is something you'll get practice with in tic-tac-toe. If you want to draw an X in the second row, second column of your board, what are the X and Y coordinates for the beginning and end of each of the 2 lines that make that X? And you'll get weird things like that. Right? And so graph paper helps with this, and lots of quick trial and error. So those are the positions of the 3 poles we want to draw. And then if there's no disks on the pole, pole length is also a flag, right? So if it hasn't been initialized, I know that the thread hasn't actually started running yet, so I just kick out of here. There's nothing to paint. Otherwise, for each pole and for each disk on the pole, I set a color code based on the disk number, and then calculate the width of the disk, and then just draw the disk as a big rectangle. And there's more mysterious calculations to figure out where the rectangle is. But this is all deterministic, right? So I know the X location of each of these poles because I decided somewhere on a piece of paper this was going to be 100, 200, 300 or something, right? And if I'm drawing the 5th disk up and I know how big each disk is, how thick it is, then this begins at 5 times that height and it ends just under 6 times that height. And if I know the disk number and I know disk 1 is the skinniest and disk 2 is bigger, and I just increase the radius of the disk by 5 each time, I can find the full length of this rectangle I want to draw. And if I know where the middle is, I can add half that to get the rightmost X coordinate and subtract half to get the leftmost. So that's all that's going on in there. And then this just sets the color based on what your disk number is modulo H. So it just makes it more interesting. And then everything else in here is just the event handlers. So the go button creates this main thread and runs the start method, which kicks off the run code. The J slider, this just sets it up, and this was all done through Window Builder, right? I didn't write any of this code. And then anytime that slider changes position, we can get the slider as a source. We can say get value, and then we use that to adjust the current speed, and so on and so forth. So the turbo button just sets a turbo flag, or toggles a turbo flag, and number of disks is 8. So let's run this. So there's our 3 poles, and if we just say go, we've got 8 disks, and they start slowly moving from the source to the destination. And it's counting moves on top, so we're at 12 moves right now. And we can speed this up. And it should take 31 moves. Sorry, it's going to take 255 moves. So let's speed it up more. So it's coming up to the halfway point where everything will be moved except that red disk, and then it moved the red disk over. And then it solves the sub problem again. And after 255, it should be completely on the second pole.
How did you decide what colors to make it?
So the disks are numbered internally, starting with 1 is the smallest disk.
Yeah, okay.
And you just take the disk number, reduce that modulo H,
Okay.
and then I just had a switch statement,
Okay.
which sets the color based on that modulus. You could also just construct the RGB color directly from the disk. So there's a 16 case, and it's pretty quick. But you can also go turbo. And then 24 is about the last reasonable one. So 24 is going to be 16 million moves to the 24th. So it takes about half a minute. And the display is not perfect, right?
Yeah, why are the lines blinking?
Because the display is not perfect. So if we refresh 30 times a second, and we have to display 16 million images, that would take a really long time, right? And we can do that. We can force it to only update during the refresh interval, but we're not putting that restriction on it, so we get flickering. But if you wanted something to be really rock solid, right? Remember the CRT with the beam sweeping across and going down and coming back up? So what you do is you paint all your pixels, right? And then when you're done painting, that's when you do all of your update to your pixel information. So the next time you paint, you see the same image across the entire display, right? Nothing changes halfway through. If while we're drawing pixels, we change some of the information, then you present an inconsistent image to the eye, and your brain picks it up as flickering. And I never let 32 run all the way, because it's 4 billion, so that won't happen.
Well, it's like, that makes sense for the discs, right? The lines are always there, but sometimes it draws the background.
Yeah, so every time it paints, it erases the display,
Oh, okay.
right? Because we have this
I guess that makes sense.
this super class. So if we get rid of that, we should get rid of most of the flickering, but it's going to look pretty unpleasant. Now we gotta find our go button. There we go.
Oh.
Alright, so it's nice and stable because it's not erasing, but
That
we've
makes
got
sense.
a weird kind of interfacing of space. But that's not without value, probably.
That's not quite as useful.
Yeah. I kind of like it, actually.
I'm just bringing.
You can still tell, you can pretty easily tell how far it's gotten, too.
Yeah.
Well, that's just because, like, it's moving, you can tell it's moving.
Yeah.
But it's really hard to tell, sometimes when things go away.
Holes
Yeah.
are still flickering though.
The poles are still flickering because the poles get drawn and then they get overwritten by the discs,
Oh,
Yeah.
right? But sometimes we're catching it in between those two events. Now we could draw 2 rectangles and always leave that pole intact. That would be one option. The other option, though, and this comes up in animations, we saw in the graphics class there was a way to control what to do when 2 lines overlap. This is where you can use an XOR. Okay, because if you use an XOR instead of a replace, and you have one line there and you draw another line, you basically combine the colors, right? And then we would always see, you know, maybe a white line or a purple line or something where the disk met the pole, as opposed to either we see a pole or we replace it with a disk. And XORs are handy when you're using that color table animation approach that we talked about briefly.
Well, at 100 million, we still have like 6, 7 more discs on the main open left.
Yeah, yeah. And 64 just doesn't work. Because I think I didn't leave enough space between the...
Oh.
but you can do it if you want. But our universe is safe for now.
I mean, we do that.
64?
Yeah.
What's 2 to the 64th?
A lot.
So what's 2 to the 60th?
It's still a lot.
Yeah, what's 2 to the 10th?
I don't even know.
How quickly can you add?
Listening
Line decimal.
Yeah.
to which one in five?
You give it to me. Base 2 to the 10th. It's a 1.
Should I calculate 2 to the 64th and see if the calculator can handle it? Which it can't.
You're doing 10th or 60th?
Is it 1024?
Yeah, I can probably do 16, 2 to 16 in my head.
Yeah, 2 to the 10th is approximately 1,000, right? It's 1K basically. And so you can get multiples of 10 by just squaring that. So 2 to the 20th is 1,000,000, 2 to the 30th is 1,000,000,000, 2 to the 40th is 1,000,000,000,000. Right, which is also 10 to the 6th, 10 to the 9th, 10 to the 12th. So 2 to the 60th is approximately 10 to the 18th. So 1,000,000,000 billion. So 16 billion billion. I've spent way too much of my life throwing around numbers like that, so can't stop thinking like that.
So how do you, gee, I just wanna look at your code for a long time now. You like put up numbers and stuff like that?
Yeah, I can post
It's
those.
like I'm trying to do something for fun, very similar to something like
Okay.
this, and it's like, man,
Yeah, I can post this.
like the speed, right?
Yeah.
How do you increase the speed? Do you
Of-
have just a wait time in every thread?
Yes. So yeah. So current speed. So it gets set with the slider, right? You can access it from here, and then yeah, I just use a sleep. So if your speed is 0, it's a sleep of 0. That's the fastest. If it's 2,500, that's like 2.5 seconds between each update. So this, by the way, this is why you get ripped off when you go to Best Buy and you buy a 3 terabyte drive, and it's not 3 trillion bytes of storage. Because the word K is a marketing term, right? So when you say you're getting a terabyte, what they actually mean is you're getting 10 to the 12th bytes, which is a lot smaller than 2 to the 40th, right? So when you get a 1K piece of storage, we expect to get 1,024 bytes, right? If we actually only got 1,000 bytes, well, we might notice that, right? So usually when you get something that's 1K, it's actually 1,024. But somewhere along the way, the marketer stepped in, and now when you get a terabyte storage, you're actually only getting 10 to the 12th bytes.
Okay.
And if you look at that in terms of powers of 2, it's a lot smaller than a terabyte, right? It's a noticeable size. So when you actually look at the storage on your disk, it's 0.997, something like that, right? And this difference between 1024 and 1,000 just amplifies as the storage goes up.
So that's a good question. Does, like, do those things refer to, if you say a megabyte, does that refer to 2 to the 20th thing?
It should, but it doesn't. Yeah, so it's somewhere along the way it started referring to
It's like,
mega meant 10 to the 6th.
because that's what it means in the metric system.
Yeah, yeah.
But if you're thinking like,
So it's legal, I
Double,
guess,
yeah.
but
I don't know.
Is it
anybody
legal in
buying a
America?
megabyte really expects, 2 to the 20th bytes.
So since we live in America where we don't use the metric system, can we sue and say that it's false
Probably
advertising?
could. I'm sure you could.
And we have the math to prove it.
And we have the math to prove it, yeah.
Case of the year.
I'm kind of surprised nobody has, or maybe someone has and we just haven't heard about it.
Feels
Just
like
throw
most
lawsuits
people
all
don't-
around and
Yeah,
it's
yeah.
like,
Most
Yeah.
people don't know about binary doubling things.
Yeah.
there are a lot of people that do though. So-
But when you go on your Windows machine and you look at the storage, it does not say 1T,
Yeah.
right? It says 0.97T, right?
Oh, I guess that's true because it was.
So you could say, hey, I was confused. Yeah, don't tell them you're a CS major if you decide to sue. 'Cause they'll say you know better. All right, cool. So this is something you'll typically use threads for, right? When you're doing graphics, displays and updates. It's a whole lot easier to sort of throw things in separate threads. Have a thread that's managing the display, have a thread that's doing the actual updating, have a thread that's managing user interactions, and then you can keep these things separate. And you communicate with one another because every time you create a thread, you're constructing the object. You can pass whatever information the object needs to be able to get back to you, and it can tell you who it is, and you know who it is, and you can exchange information through shared memory that way. Something else I was going to say along those lines. Thread. Oh, and Swing is doing this all the time, right? When we do anything with Swing, we've already got some threads in play, which is why when your main method exits, your program continues to run, and it's because the threads still hang out. So we always have something like this. When we create a J-frame, it gives us a main method. And it's basically, this is getting run as a thread, right? So it's got a run method, and it does whatever you tell it to do. And it usually just creates your frame and then exits. But it's threaded stuff happening. All right, so tomorrow let's start looking at things like list arrays, linked lists, hash maps, hash tables, and other built-in data structures that we'll find useful. And this will take us into talking about trees next week.